we're delving into the intricate workings of traffic routing, as seen in tools like Google Maps. Understanding how real-time traffic is assessed and predicted is crucial for optimizing travel and improving urban planning. The approach hinges on various components: live speed data combined with historical averages, adjustments for incidents like construction or accidents, and the understanding that travel times fluctuate throughout the day. We're breaking down traffic dynamics over a week, which translates into a detailed framework of over 2,000 time steps for each zone. This is feasible due to the manageable number of traffic zones we are examining, around 25 to 60. Each of these zones will be modeled based on several factors, such as the base population and how it varies by hour and day type, along with unique multipliers for different zone roles, which capture unexpected events or fluctuations. The roles defined for our zones are quite realistic and diverse, including downtown areas, campuses, residential neighborhoods, and tech corridors. This diversity enriches our model, allowing us to capture a wide range of traffic behaviors. We also plan to incorporate additional variables like incidents that might cause sudden increases in traffic within certain zones, especially in high-traffic areas. Similarly, we will account for events that typically draw crowds to parks or downtown regions, as well as possible weather-related effects that could alter traffic flows. As we move ahead, we'll be looking at how these modeled densities translate into actual traffic predictions, enabling us to create a more responsive and accurate routing system. By incorporating all these factors, we aim to paint a comprehensive picture of traffic behavior, which is integral for navigating and enhancing urban mobility. The next cell will likely build on this modeling framework to simulate actual traffic scenarios, allowing us to see how these variables interact in real time. Cell 2. In this cell, we're laying the groundwork for generating a week's worth of realistic population density data tailored to specific zones in Boulder, Colorado. This matters because understanding how population density fluctuates over time can help with urban planning, transportation modeling, and resource allocation. We start with a synthetic zone creation function that defines various areas in Boulder, each with unique characteristics such as role, base population, and geographic coordinates. The code generates some initial zones like downtown Pearl and CU campus, then adds more generic zones to ensure a richer dataset. Key variables here include zone ID, zone name, and base pop, which essentially represent the foundational attributes of each zone. Next, we have the daily profile function, which creates a smooth density curve across a 24-hour cycle. It incorporates different peak times, like the morning rush and evening activities, providing a realistic representation of how population density might fluctuate throughout the day. We also define a roll time multiplier that adjusts density based on the role of each zone and the time of day. This accounts for varying patterns, such as more activity in retail areas during weekends. Then, as we generate a week's worth of density data, we pay attention to several factors. The code uses randomization for minor variations, implements event bumps for specific roles during peak times, and models noise to mirror real-world uncertainty. A noteworthy part of the code involves creating visual indicators for density levels, categorizing them into traffic colors like red, orange, and green based on normalized density values. This allows for quick visual assessments of traffic density. It's essential to be aware of potential pitfalls, particularly around the choice of frequency in generating data. The original code suggests that a finer resolution would be ideal, but performance issues prompted the use of a coarser time interval. As we move forward to the next cell, we can expect to take this density data and apply it to models that simulate traffic flows or visualize the intensity of activities in each zone over our generated week. This will deepen our understanding of local dynamics and potentially influence real-world decision-making. Cell 3. In this cell, we're setting the stage for a deeper understanding of patterns in our dataset by analyzing normalized density according to both the hour of the day and the day of the week. This analysis is crucial because it helps us visualize shifts and trends in our data across different times, revealing any cyclical behaviors that may emerge. To start, we adjust our display options to ensure that all our data is visible when we present it. This ensures we don't miss any pertinent details in our analysis. We then extract the weekday names and hour information from the timestamp column in our dataset, enabling us to categorize the density measurements effectively based on time. Next, we reorganize our data using a pivot table. This table computes the average normalized density for each combination of weekday and hour, effectively summarizing our data into a more manageable format. With the reset index function, we transform our grouped outcome into a format that's easy to manipulate. By pivoting this structure, we create a table where weekdays form the index and hours become the columns, allowing us to see average densities at a glance. It's also worth noting how we order the weekdays to follow a conventional sequence, starting from Monday to Sunday. This logical arrangement makes our heat map interpretation more intuitive. Lastly, we display just the initial portion of our pivot table, giving us a sneak peek into the insights we anticipate uncovering. As we prepare to move to the next cell, this foundational setup paves the way for visualizing our findings through a heat map. This visualization will help us identify clear trends and anomalies, enhancing our overall understanding of how density varies by time. Cell 4. In this cell, we're using Plotly Express to visualize data with a heat map, which is a powerful way to represent complex quantitative information visually. Specifically, we're examining the average relative cell density, normalized by day of the week and hour, to understand patterns in the data more intuitively. The key variable in this visualization is the matrix we've created, referred to as pivot, which aggregates our data across two dimensions, the days of the week and the hours of the day. This allows us to see how cell density varies at different times, highlighting any trends or anomalies that might exist. The choice of a heat map is crucial here, as it enables us to quickly identify areas of high and low density through varying colors, essentially making the data more digestible. We set the aspect ratio to auto to ensure that the cells in our heat map display proportionally, which can help prevent misinterpretation of the data due to distortion. The title we've added provides context, indicating what the viewer should be looking for, and we've adjusted the dimensions of the figure to enhance visibility. It's essential to keep in mind that visualizations can sometimes introduce biases based on color scales, so choosing an appropriate range for our heat map is vital to ensure that patterns in the data are accurately represented. By displaying this information clearly, we can foster better insights into how cell density behaves throughout the week. As we move to the next cell, we will likely dive deeper into interpreting this heat map, drawing specific conclusions based on trends observed in our current visualization. This will help us understand implications or actionable insights that can be derived from the data. Cell 5. In this cell, we're diving into a visualization that compares the relative density of different zones over time, specifically focusing on downtown, campus, and corridor areas. Understanding these patterns is crucial for urban planning and resource allocation, enabling us to see how foot traffic varies across key locations. First, we're filtering the dataset to only include entries from specific zones, namely downtown and its surrounding areas, which are represented by identifiers like Z01, Z02, Z08, and Z09. This step allows us to isolate the data that is most relevant to our analysis. By copying the filtered data into a new variable called sample, we ensure that we can manipulate this subset without altering the original dataset. Next, we're utilizing Plotly's Express library to create a line chart that visualizes this density data. Here, the x-axis represents time, specifically the timestamp variable, while the y-axis reflects the normalized density values. Each zone is color-coded, making it easy to analyze how different areas compare over the course of the selected time period. The line chart helps in capturing trends and fluctuations in density, which can be indicative of varying levels of activity or crowding. It's important to acknowledge that while the chart visually conveys these trends, the interpretation relies on accurate timestamps and normalized density values. Any discrepancies in these data points could skew the results and impact your conclusions. Finally, as we wrap up this analysis, we'll use our insights to inform the next steps, which likely involve comparing these patterns against other variables or datasets. This will deepen our understanding of the dynamics at play across these zones and both inform and enhance our future modeling efforts. Cell 6. In this cell, we're creating a visual representation of traffic densities across different road segments, categorizing the traffic from low to high using color coding. This kind of visualization is crucial for understanding traffic patterns in an area, which can aid in urban planning, congestion management, and overall transportation efficiency. We start by defining a geographical area using coordinates and generate a directed graph of the road network in that area. This graph is enhanced with travel speeds and times, ensuring we have a complete picture of traffic conditions. It's important to confirm that these travel times exist. Thus, we explicitly set a default travel time in case any edge lacks this information. Next, we take a snapshot of the traffic density data, extracting a specific timestamp that allows us to focus on a particular moment. This snapshot gives us a filtered view of our data, which we will subsequently map to our road segments. To prepare for the mapping, we convert our road network graph into a geodata frame, which structures our data efficiently for spatial analysis. A significant step involves calculating the midpoints of each road segment, which will serve as reference points for density measurements. If a straight line geometry can't be obtained, we compute these midpoints by averaging the coordinates of the endpoints, ensuring we have a reliable position for each segment. Using these midpoints, we apply a k-nearest neighbors algorithm. This technique helps in smoothing the density values derived from nearby zones, allowing us to better represent traffic density on the edges. Here, we need to be cautious of potential issues with sparse data, making sure that our distance cutoff effectively avoids introducing inaccuracies at the edges of our analysis. After smoothing the density data, we categorize traffic density into colors: green for low traffic, orange for moderate traffic, and red for high traffic. This classification is determined by the quantile values, providing a relative view of traffic conditions that is easily interpretable. Finally, we visualize the road segments using Plotly's scattermap box. For each color, we create lines on the map that represent the corresponding segments and their traffic conditions, enhancing clarity in the presentation. The end result is a dynamic, interactive map centered on the area of interest, allowing users to explore traffic as it changes over time. Looking ahead, the next cell will likely build on this visualization by incorporating real-time traffic data or exploring additional analytical metrics for deeper insights into traffic flow and urban mobility. Cell 7. In this code cell, we are focused on creating a dynamic visualization of traffic densities throughout the day, which can be adjusted interactively via a Plotly slider. This is crucial because it allows users to observe fluctuations in traffic patterns based on time and day of the week, enhancing decision-making for urban planning or navigation. The process begins by utilizing existing graph structures to extract nodes and edges, which are essential for defining the road network. We then calculate the midpoints of each road segment, allowing us to effectively represent traffic data at specific spatial points. The midpoints are derived from the geometrical data. If that information is missing, we use a fallback approach that averages the coordinates of the endpoints. This lays the foundation for understanding where traffic densities will be plotted. Next, we pre-compute the coordinates for the polylines that represent each edge of the road network. This efficient approach ensures that we only need to compute these once, saving computational resources during dynamic updates. Following this, we establish static zones that correspond to unique geographical locations, which are crucial for mapping the traffic data against the established road network. An important step involves creating a KD tree to quickly identify the nearest zone for each road segment midpoint. This allows us to efficiently query the zone density data without repeated searches, thus enabling smooth, real-time updates as the user interacts with the slider. We also prepare a dictionary to store traffic density information by time, which ensures rapid lookups. Finally, we establish a mechanism to classify edge densities into different traffic levels: green for low, orange for moderate, and red for high traffic. This classification will define how the traffic is visually represented on the map. As we move forward, the next cell will likely focus on bringing all these components together, creating the interactive map that showcases the varying traffic conditions over time. Users will be able to effectively visualize changes and make informed decisions based on this rich set of data. Cell 8. In this cell, we are setting up a foundational network graph for Boulder, Colorado, using the OSMNX library. This is crucial because it allows us to analyze transportation routes by incorporating travel dynamics like edge speeds and travel times, giving our model a more realistic basis when we explore routes later on. To start, we define the area of interest, which is Boulder. The next step leverages OSMNX's capabilities to fetch a street network specifically designed for driving. Importantly, we've chosen a simplified version at this stage to ensure that our processing remains quick. This will allow us to test and expand our analysis later without overwhelming our resources initially. After establishing the graph, we enhance it by adding edge speeds and travel times. This is accomplished through two dedicated functions from the OSMNX library, which automatically calculate and assign these parameters for each edge in the network. It's vital to understand that these values can significantly influence routing decisions. Specifically, we choose to establish a variable called TD time, which stands for travel time, as our parameter for routing weights. This dictates how the algorithm will prioritize different routes based on expected travel times. In the loop that follows, we iterate through each edge in the graph to assign the calculated travel time, ensuring that if no travel time is available, we revert to a default value of 1 second. This safeguards the operation from potential errors while maintaining the integrity of our data. Finally, we provide feedback on the graph's structure, including its type and the number of nodes and edges, allowing us to assess how comprehensive our network representation is. This information not only confirms successful execution, but also hints at the complexity of Boulder's transportation landscape. Looking ahead, the next cell will likely build on this groundwork by applying routing algorithms to find optimal paths through this network, utilizing the travel time data we just established. This progression will deepen our understanding of transportation dynamics in Boulder. Cell 9. In this code cell, we're generating a list of all global variable names that begin with the letter G. This is a useful approach when we want to quickly identify specific variables in our current workspace, particularly when refining our analysis or debugging. At the heart of the cell, we're using a list comprehension, a concise way to iterate through every key in the global namespace, which is accessed via the built-in function globals. This function returns a dictionary representing the current global symbol table, and by applying a key filter, we can focus on the variables that meet our criteria. Here, we're particularly interested in names that start with G, converted to lowercase to ensure that our check is case insensitive. This can be incredibly handy when working on larger projects where variable names might not always be uniquely descriptive. It allows for a more streamlined workflow by enabling us to quickly see all relevant variables starting with a specific letter, which can enlighten our understanding of what variables might be intertwined in our calculations or functions. However, learners should be mindful that this approach reflects only the current global scope, meaning any variables scoped within functions or classes won't appear in our results. In terms of expected outputs, the cell will produce a list that we can either print or further manipulate, depending on what we need to do with these variable names. This gives us a snapshot of our environment, but it also highlights the importance of organization in coding. Maintaining clear and consistent naming conventions can significantly ease this sort of exploration. Looking ahead, The next cell will likely build upon this list of variables by performing some actions with them, perhaps filtering further or executing functions based on those names, thus enhancing our analysis or tweaking our models. Cell 10. In this cell, we're using a bit of JavaScript to modify the metadata of our Jupyter notebook, specifically targeting the widget's functionality. This step is essential for some users who may want to disable or modify the way widgets interact with the notebook environment, perhaps for reasons like performance optimization or usability adjustments. Here, the main action occurs with the display function importing from IPython, allowing us to execute JavaScript directly. The JavaScript snippet essentially clears any existing widget's metadata by setting it to undefined. This operation's importance comes into play when managing how interactive elements appear and function within your notebook. By removing that metadata, you would prevent certain interactive features associated with widgets from functioning, which could be beneficial if they are unnecessary or causing confusion in your current analysis. It's crucial to note that while this action can streamline the interface, it may also lead to unexpected behavior if you have other cells relying on widget functionality. As you proceed, be mindful that during execution, the output will not give you feedback. It's more of a behind-the-scenes adjustment. This cell doesn't produce a visible output, which might be a bit disconcerting for someone expecting immediate results, but it underscores how the notebook can be subtly controlled. Moving forward, we'll likely build on this by examining how to work with Jupyter's interactivity more dynamically, potentially restoring some widget functionality, or exploring new capabilities that leverage this cleaned-up environment. Cell 11. In this cell, we're developing an interactive tool that allows users to recommend alternative routes in high-traffic scenarios, enhancing the navigation experience significantly. By utilizing the OSM&X library, we can build a detailed road network that incorporates time-dependent costs based on travel conditions. Now, let's delve deeper into the core functionalities. The tool enables users to select an origin and destination on a map. With this input, the system calculates not only the optimal route, but also generates 3 additional alternatives. Key steps involve assessing travel time and distance, factoring in congestion penalties, and ensuring the routes differ enough to give users a variety of choices. This is crucial because identifying alternative paths can help drivers avoid congested areas, ultimately saving time and reducing frustration. The utility functions in the code are quite pivotal. For instance, the simplify coords function optimizes the representation of route coordinates, which is especially beneficial for handling large datasets without overwhelming system memory. Similarly, path2coords extracts the coordinates from a calculated path and prepares them for visualization on the map. Important variables like base W represent the minimum edge weights, ensuring efficient route calculations while accounting for dynamic traffic conditions. As we examine the routing process, k-alt-routes-fast stands out. This function generates multiple potential routes using a dynamic weight system to adjust for previously traversed edges, thus ensuring diverse alternatives. The method takes into account variable travel conditions, enhancing the adaptability of the tool in real-world scenarios, which could be a significant consideration for users who frequently navigate through busy areas. Moving forward, this cell sets the stage for the next phase of our project, where we'll expand these functionalities, potentially integrating more user-friendly features and visual aids. This would further augment the interactive map experience, making it even easier for users to choose their preferred routes efficiently. Cell 12. In this final cell, we're wrapping up the analysis and shining a light on the conclusions we've drawn from our work. It's crucial to take a moment to reflect on what we've accomplished and ensure that we understand the implications moving forward. Throughout the notebook, we've gathered data, performed calculations, and created visualizations that have guided our exploration. By synthesizing everything, we can pinpoint the key takeaways and understand how they fit into the larger picture. This final cell acts as a summary that reinforces our findings and solidifies the knowledge we've built. As we review our results, it's important to think about the assumptions behind our analysis and where potential pitfalls may lie. For example, have we properly accounted for any outliers or considered how our data might vary under different conditions? By critically examining these aspects, we can bolster the robustness of our conclusions. Moreover, thinking about future applications is essential. How can we use what we've learned to inform decisions or further research? There are always new questions to explore, and our analysis serves as a launching pad for those inquiries. Looking ahead, the next steps might involve deeper exploration into the underlying trends we've identified, or even expanding our dataset to see how our findings hold up in different contexts. This process of continual learning and adaptation is what drives us to become better analysts. So let's be excited about where this journey will take us next.